and say that's equal to delta H over delta V times integral dt over t is natural log of t. And we found that when we evaluate that between the initial and final conditions, we get t final over t initial. So along the solid-liquid boundary, we're allowed to make this approximation that delta V, the change in volume, isn't necessarily a function of temperature and pressure, because solid-liquid volume changes aren't that subject to pressure and temperature change. You change the pressure of a substance very slightly, a solid or a liquid, its volume only changes a little bit. You change the temperature of a solid or a liquid, its volume only changes a little bit. So we can essentially pull those guys out of the equation, simplifies our math for us a little bit, and we get this expression. This expression essentially tells us that the pressure is exponentially dependent on the temperature. But that simplifies. This guy can be simplified by using the relationship that, well, first of all, let me recast this. T final for an infinitesimal change in the temperature is equal to T initial plus dt. So this expression simplifies to delta H over delta V times the natural log of T initial plus dt over T initial. And this guy, for this expression, essentially, can be converted into one that says, or one that says 1 over dt over t. Ti over Ti is 1, dt over Ti is just dt over Ti. So this argument can be turned into this term, and that guy, if you look at it in a series expansion, natural log of 1 plus something that is much less than, how do I write this? Much less than 1 is just that term. So delta H over delta V, line Ti plus dt over Ti is just equal to delta H over delta V times dt over T. And so your pressure ends up being, we had a natural log argument for this guy, but by using that series expansion, we find out that we can recast it in a term that says that essentially the change in pressure is linearly dependent on the change in temperature. So the change in the equilibrium pressure for one of these guys varies linearly with the change in pressure for the solid to liquid equilibrium. What about the liquid to gas boundary? You guys are quiet. Must mean that I'm not articulating very well. That's okay. I forgive you. How are we going to look at that liquid to gas boundary mathematically? Is delta V going to be kind of independent of pressure and temperature changes for liquid to gas transition? What's the volume of the gas do given changes in temperature and pressure? If you take a solid or a liquid, and you change temperature and pressure, how much does the volume change? Not a whole lot, right? Very small changes in volume. But when you look at a gas and you start changing its temperature and pressure, we know, just from experience, the gas's volumes change very, very rapidly and very readily with temperature and pressure. And so we have to kind of use a different mathematical approach to look at the changes in, to map out the equilibrium positions along the solid and solid to gas and liquid to gas transitions. So we start with the same equation that we had before. dP over dt is delta H of the transition over T times delta V of the transition. This time, delta V is V final minus V initial. If your final state is your gaseous state, and your initial state was some condensed state, solid or liquid, then the gas phase volume, the gas molar volume, is going to be the dominant term in that difference. And so delta V of the transition simplifies to V of the gas minus V of the liquid or solid, depending on which curve we're along, right? Either way, it's approximately equal to the V of the gas. Volume of an ideal gas is RT over P, and so the expression that we have here changes to something that looks like this. RT over P minus 0, you flip that P up, you end up with P in the numerator and RT squared in the denominator. And so we have this differential equation that says dt over dP is P delta H over RT squared. You saw last time that we can move all the appropriate variables to one side of the equation or the other and take the integral. So we move the P into the denominator here. We take the T, we move it up to the numerator there, and we get the expression that says dP over P is delta H of transition times dt over RT squared. We can integrate that from initial to final pressures and temperatures and get an expression that relates P and T. In taking this integral, we're assuming that delta H of the transition is independent of temperatures. And so we saw that early on in the class that enthalpies aren't necessarily independent of temperatures, because as temperatures rise, different degrees of freedom become available. But we're making the approximation in this derivation that we're in a range of temperatures where delta H is essentially constant for the process. So we end up pulling that delta H out of the integral, and we're integrating essentially dt over t squared, right? That ends up being the integral of, ends up being negative 1 over t evaluated from initial to final conditions. We integrate dP over P, we get natural log of P final over P initial is equal to negative delta H of transition over R times 1 over T final minus 1 over T initial, right? And this equation then is the equation that maps us from one point to another along any of these boundaries. That equation can be used for the solid to liquid transition, or it can be used for the liquid to gas transition. And it's a very good approximation to how the pressure will vary, how the equilibrium vapor pressure is going to vary with a given change in the temperature. It's called the Clausius-Clapeyron equation. Go ahead.
So you said we can use this for any solid to liquid or liquid to gas transition, but can we use it, would it just be like negative if we were going liquid to solid or gas to liquids transition?
Sure.
Yeah?
Yeah, if you move in the opposite direction.
Okay.
So we have two kinds of mathematical approximations to the positions along each of these curves. The Clausius-Clapeyron equation describes the liquid to gas, the solid to gas and the liquid to gas curves, and the one over there where we looked at the changes in volume as being constant and pulled them out of the integral, that equation maps positions along these boundaries, right? The solid to liquid boundaries. What about the relative slopes of this line, the solid to gas equilibrium line, and the liquid to gas equilibrium? Which one of those has a larger slope?
Solid gas.
Just by looking at the way I've drawn it, it looks like solid to gas. Can we figure out an argument for why that might be the case?
Solid's often the most condensed state of a substance, right?
Yeah, so our equation told us that dP over dt, the slope of that thing, is equal to delta S, the transition, over delta V of the transition, right? Which of those transitions is going to have the larger delta S? We know that there's an increase in delta S moving from solid to liquid, and there's a subsequent increase in S moving from liquid to gas. So we imagine that moving from here to here would involve a larger increase in entropy than moving just from the liquid to the gas over there, right? So delta S for solid goes to gas is larger than delta S for liquid goes to gas. And so looking at that equation, we can provide an argument for the magnitudes of those slopes. There's an equation in your book. There's something that's spoken about called Troughton's rule. Have any of you read the chapter? What's Troughton's rule about this? Troughton's rule is kind of weird, and when I read it, it caught me off guard for a second. The more I thought about it, the more I decided it made sense. Troughton's rule says that for a liquid to gas transition, delta S is approximately equal to 95 joules per mole Kelvin. It's 90, 95, it says something like that. I encourage you guys to read the chapter. 85. Yeah, depending on what book you pick up, they'll list different values for Troughton's rule. That's why I wrote 95. One book I have says 90, the other one says 85. I think I went on a limb by saying 95. What's it?
Is that for water or just any substance?
That's what we're getting at right now. So that is for most substances. For most substances, the change in entropy for the liquid to gas transition is going to be about 95 joules per mole Kelvin, right? It doesn't hold for a substance that has very, very strong intermolecular forces. Something like water, this relationship isn't going to hold. What does that mean? What are the different components that go into an entropy change?
Intermolecular forces.
When volume increases, does entropy increase?
Yes.
Right?
And how much space everything up.
And so, for any substance that's in condensed phase, like liquid or gas, when its volume increases, there's going to be some inherent entropy increase just based on the amount of volume, or the amount of the increase in volume, right? what happens when you put heat into a substance? Does the entropy increase?
Yes.
So a substance that takes on a lot of heat in moving through a phase transition is going to have an increase in its entropy based on how much heat it's taken on. Now it's got a bunch of energy that it needs to store amongst its different modes, and so the more heat that you have to put into something, the larger the entropy increase. It turns out that, so for any substance going to gas phase, assuming that it behaves as an ideal gas, the volume change from liquid to gas or from solid to gas is going to be about the same. And so the increase in the entropy that you get from that volume change is going to be relatively constant, assuming that your substance behaves as an ideal gas. Substances, pardon me, require more heat, though, to drive them into the gas phase. And so the Q term, the Q over T term, or the heat-dependent effects on the entropy will be greater than they are for a substance that requires less energy to move off into the gas phase. For most substances, the intermolecular forces are about the same that hold them into the condensed phase and the liquid phase, liquid phase. And so the amount of heat is approximately equal, and the volume change is about equal. And so for most substances, that total delta S term just happens to be about constant. Is that weird? Does that seem weird to you? Yeah, it seemed weird to me too. But apparently that's the case. It's just essentially saying that the strengths, the relative strengths of those intermolecular forces in the liquid phase are about equal. If they're not equal, then you've got a situation like with water where the delta S is going to be larger for that phase transition. There's a problem in your homework where they ask you to estimate delta H of a transition, and they end up with, I looked at the answer key, and the answer key they want you to go to a table of delta S's and pick out delta S for the particular substance. I think it was, let's dig that homework problem up and look at what we talked about. Number 9, right there, it says the normal boiling point of benzene is 80.1 degrees Celsius. Estimated its delta H value and its vapor pressure, 74. So this homework problem, before I write this out, this homework problem, they tell you the boiling point. The boiling point is 80 degrees Celsius. What they're getting at is that you're going to use this delta G is equal to delta H minus T delta S equation. At equilibrium, at the boiling point, what is delta G? 0. So that guy goes to 0. And so then you can say that delta H is equal to T delta S. Yeah? They were kind of asking you to look up in the book and find out that benzene has a particular delta S, and to plug in that delta S value to get a delta H value. Based on what we just talked about here with Troutman's rule, can you figure out another way to solve that problem? What's that?
Call it 85 or
Call it 85 or 90, right? Benzene is not one of those things that has, particularly strong intermolecular forces, and so its delta S for that phase transition is probably going to be, I'll call it 90, since that's closer to, your book says 85, my other book says 90. You just plug in 90 joules per mole Kelvin based on Troutman's rule, and get an estimation for the delta H of that transition.
Are there any exceptions?
Oh, there's all kinds of things have really strong intermolecular forces. Water is probably going to be the biggest there, but any kind of a molecule that has a dipole in it, or the ability for hydrogen bonding or anything like that, any kind of an increased like electrostatic effect that's going to increase the intermolecular forces. Something like benzene, where you've got a hydrocarbon that's mostly, its intermolecular forces are mostly whatever van der Waals forces, then you're going to end up obeying Troutman's rule. But anytime you change the structure to increase electrostatic attractions, then that rule is going to deviate. And so you can probably look at a substance and just take a glance at it and say, is it polar, is it non-polar, does it have the ability for hydrogen bonding, and decide whether or not Troutman's rule is going to apply for that substance. In fact, that would be a really good test question, right? If I wanted you to estimate a delta H for different substances, and I gave you one that had hydrogen bonding and one that didn't, and asked you which one you could use Troutman's rule on. Same problem. So how are you going to answer part B? The vapor pressure at 74 degrees Celsius. Yeah. So from there, you're given a delta H value, or you're not given a delta H value, but you go about finding the delta H value either using Troutman's rule or looking up the entropy of that phase transition for benzene, and you come up with a delta H. That allows you to move back to this equation, and say that the natural log of the final vapor pressure over the initial vapor pressure is going to be delta H transition over R times 1 minus T initial over 1 minus T final. So assume that initial pressure is 1 atmosphere of pressure for the normal boiling point. Normal boiling points are always defined as the temperature at which a substance under 1 atmosphere of external pressure reaches its equilibrium. So your P initial on that guy is going to be 1 atmosphere, your P final is going to be whatever that vapor pressure ends up being when you change the temperature to the final value. Yeah? Glance over these, see if there's any key thoughts that I'm missing here. All right. I'm going to play around with something for a little bit.
Any questions, Ron? Started it early. Try to do it over the weekend.
Sorry, I gotta find the question I was gonna ask you guys to answer. I'm not seeing it right now. All right, we'll do a different problem. Let's try this one.
Hungry.
Because you got like 61,000. 61,000. Do it as per day, make it delta H. Okay, we got